You're online. Okay, so it says that I'm online.
Yep.
Can you double check that it is online? And how is my voice?
Can you say something?
Okay, so mic check, mic check. So it doesn't look, it looked that there is something a little off in the screen itself. Is it? Can I see how? Yeah, not the way that I would like that to see. Oh, but yes. How come it's not? Because it's supposed to be entire display. Entire display, display capture. This one, display. Hey, how is it? Can you see that this is then better? So there's a few seconds delay, but it looks pretty. It looks fantastic. So if I stand up, so can you still see my head? I guess not.
No.
So it's cutting my head off.
The delay is too low.
So it could be 60 seconds delay. No, it's not, because I say 60 seconds, a little less, way less than a 60 seconds back. Yeah, just to raise that a little bit, because it cuts this part of my head, and then it's good. Or you can just use that screw to put it on. Perfect. Perfect. Okay, guys.
Okay. So, do you need me?
No, I don't. Respect. So it's going to be hour and a half, something fun. I hope that this is going to be a highlight of your week every time we meet. So today we're going to discuss a little bit unpleasant subject matters. But once this week is done, then we're going to move on to what I promised earlier, something a bit more pleasant. But first something unpleasant and then pleasant. How that sounds? Yeah, why not? Why not? First work and then pleasure. All right, now there's, let me count, 1, 2, 3, 4, 5, 6 screens. So you shouldn't, but they're still blinking. How come they're blinking? All right, but anyway, so we are able to see my presentation in 6 different screens, and still we are having a bit of the problem because they are blinking. I hope that that's not going to be a problem to raise lecture. So we're going to wrap up the deal about the 3-dimensional multibody system dynamics. Honestly, it's not about the 3-dimensional multibody dynamics, but it's more about 3-dimensional kinematics, because I would like you to be aware of what's the big deal about the 3-dimension and why that is so much more complicated than anything related to planar simulation. And that's something that is good you to be aware of, because life is 3D, it's not planar. And something that if you like to use some of the tools that are heavily used in computer games, like some of the softwares and so on and so forth, you always need to deal with the 3-dimensional rotations. And the way they are usually treating the 3-dimensional rotations are based on quaternions. And that's something we can go back what we discussed a week back, and then we're going to close, I'm going to wrap up the discussion about, what about if using 4 parameters to describe the body rotation. And the 4 parameters, generally speaking, those fall under the category calling quaternions. And now it's quite surprising that if you look at how many papers, how many publications there are that are touching the subject matter of quaternions, there's a lot of it, still a lot of it. And even more surprising is this, that this subject matter is not closed in science. There are still papers, quite a bit of them, that are coming each year telling that, okay, now I eventually figure out the better way to describe the rotations in 3-dimensional space, better way to describe it. And again, let me emphasize describing. It's not unclear that the body can rotate in 3 different ways. That's clear case, but how to describe that mathematically in a way that the method is not suffering from singularities, that's something that is still under the discussion, still under the research. And there are some promising methods like Lie group, which is an entire new mathematics, which is based on 3 parameters and seems to be one of the most efficient ways to go. For sure, we are not going to touch the Lie group. We are not going to touch any of these super advanced technique, but we can just look at the basics. The basics, let me correct myself, like basics of the basics is a Rodriguez equation. And then like a bit more advanced from Rodriguez equation is Euler parameters. And that's where we're going to get started today, Euler parameters. But first thing first, what is it we learned a week ago? A week ago we learned that 3-dimensional kinematics is no different comparing the planar kinematics. Same story, but the difference, of course, is the fact that dimensions are enlarged. And they are enlarged in a sense that if you look at the vector R here, the ones that is describing where the body reference coordinate system is located with respect to global coordinate system, this vector R consists of 3 components that are projections in a global X, Y, and Z coordinate axis. And then, of course, a rotation matrix that is going to be 3 by 3 matrix. And we can describe this already using 2 different alternatives. We can describe it that using Euler angles that was based on successive rotations, or Rodriguez equation that is the concept that is based on one vector that is rotating using assisting vector to make it happen. So let me see if I can find a stick here. No sticks. How come there is no longer sticks in this lecture room? So how can I penalize you guys if you're not behaving well? Where is it? Where? Behind of me. There. Of course, this is a mandatory equipment for each of the lecture room because if you don't know the correct answer, you need to put your fingers in a table, and then I'm going to use this as a tool to penalize you. So this is kind of the must-have thing. All right, so there is the idea was that having this vector, random vector in the random length, random orientation, and then you're going to rotate this vector. And you're going to make it happen with help of the vector v. The vector v is unit in a length. So what you're going to do with these 2 components, you're going to combine them such the way that the vector v goes in the origin of this original vector, like this. This is a configuration. And then you're going to do a rotation, and the amount of rotation is theta. That's it. And now you need to just find the relation between where the original vector is located at, this one, and where it's eventually rotated to. And once you see this relation, that's going to give you the rotation matrix that will have a dimension 3 by 3, but it will consist of 4 parameters. 4 parameters. All right. So that's going to be something that is called Rodriguez equation. One more component, going back to this equation, the last component is vector u bar. That too consists of 3 components. And of course, because it is a function, let me correct myself, projection of body x, y, and z coordinate axis. And that's what we learned. This is what we learned already in the preschool. This is what they're explaining already in early age. This is Euler angles. And they explain this in early age because this is simple procedure. It's based on successive rotations. It's not overly complicated. And the successive rotations typically goes in such the way that you have a first rotation around the z coordinate axis. Amount of rotation is psi, and then the second rotation is around the x coordinate axis. Amount of rotation is theta, and one more rotation is again twice rotated z coordinate axis, and amount of is 2. And that's it. And then you're happy with my pronunciation? Yeah, that's what I was thinking too. So these are the rotation matrices describing each of these 3 rotations. You multiply them together. That's your description in 3-dimensional space. This is what we discussed when we closed a week ago. So now we have the method that is based on 4 parameters. 4 parameters. What are these 4 parameters? Of course, the vector v consists of 3 components, vx, vy, and vz with respect to global coordinate axis. And then we have 4th parameter that is angle theta. So that, a total of 4. And again, never ever think that the body can rotate in 4 different ways. That's not possible. At least in a kind of like reality where we're living at. So in the reality we're living at, the body can rotate in 3 different ways. That's it. That's it. Now there is a conflict here, because if the body can rotate in 3 different ways, and we're using 4 parameters to describe these 3 different rotations, there is something is off. You know, there's too many parameters. And there's too many parameters, obviously, because 4 parameters. But again, keep in mind that they are not independent. They are coupled. And because they are coupled, there's one constraint. And it's the same way that in a multi-body system dynamics, if you have originally, let's say, 4 generalized coordinates, one constraint equation, so eventually you have 3 degrees of freedom. Same holds here. Yes, you do have 4 parameters in the beginning. Yeah, that is the case. And then you have one constraint, which is the fact that this vector v is unit in a length. That's going to be your one constraint, giving you a total of 3 degrees of freedom. That matches with the fact that the body can rotate in 3 different ways. So that's how it goes. All right, so again, remember this is this one here is the skew symmetric form of a vector. So it's nothing too special. A skew symmetric form is a mechanical thing to do. So there's nothing big surprises there. Problem of this method is that these 3 variables don't have a clear physical interpretation. So if I give you these parameters, components of vector v and angle theta, there is going to be no way to clearly understand how is going to the body orientation. It says, usability of this method is very low. It's very low because parameters don't have a clear physical interpretation. Different than this guy. Because if I give you these c, theta, c, whatever parameters, you can tell me immediately how is a body orientation in a space. That's clear. And if I give the same, well, not the same, but the different parameters, v1, v2, v3, and angle theta, you don't know how is a body orientation. That is hard to understand. Computers, they love this procedure. And why they love it? They love it because this method, based on 4 parameters, do not suffer with singularities. There is always clear interpretation of what rotation is what. They never get confused, never. All right, so that's where we are, and then here is this constraint equation. So the length of vector v have to be 1 unit in a length. That's it. That's the constraint. All right, now my first in-class quiz today, and the participate in-class quizzes. So what you need to do is that you need to log yourself to Socrative, and those ones that are participating online, you can take a picture of this QR code using your mobile phone, and that should take you immediately to this Socrative website. In the Socrative website, you need to enter by using your student ID number. And if you're entering manually, make sure you are putting your room number to be LUT26. LUT26 refers to the fact that we are in LUT, and year is 2026. All right, so room is different than it was when we met last year, so make sure you're using the right kind of the room, and that's the way to look into the Socrative. And my first question is this. In Rodriguez equation, rotation is described by 4 parameters, and these are the 4 parameters. These 4 parameters are coupled because angle theta is small, vector v is unit in a length. We are assuming the body to be rigid. Parameters are not coupled because body can rotate in 4 different ways. Remember, any recollection? This is what we discussed last week. So what I'm expecting no less than 100% success rate. So if I'm going to score less than 100%, I'm going to just walk out, go back to my office, lock my door, and never come out of my office. Okay? So you need to play with me, please, please. Careful now, careful. So don't just randomly enter your answer, but think, because that can have a serious consequences to my life. All right? So should we take a look? You guys were able to enter your answer? So it was the room and everything went smoothly.
Yes.
Good thing. All right, so let me see where is my. Let me take this new window. Where was it? Because it was a visible little while back. Now I just don't see it anywhere here. Huh. Where was it? And this guy is not working. Oh, now he's connected. Okay, so let me lock myself one more time. Teacher locking here. So there's something live here. Cancel. I just need to find a proper window to log in this place. So it's hidden somewhere. Can you see? There is only this one. Live results here. Oh no, I don't want to show. I don't want to see this one here. Guys, I'm afraid that what I need to do is that I need to because I need to launch this again. Exit ticket. And if I launch this again, it's gonna cancel this activity. So can you please log in again and enter your answer one more time? Because I need to just do this because the browser was closed. I don't want to do this either. Hold on. I need to finish the activity one more time. I need to do this. Open teacher's pad. This one. Now you guys good to go. All right. So again, same question. Why Rodriguez equation? Let me correct myself. How these four parameters using a Rodriguez equation, how they are coupled, and the answers are possible options are angle theta is small, vector v is unit in a length. We are assuming body to be rigid. Parameters are not coupled because the body can rotate in 4 different ways. All right, and then let me take a look at how many answers we have. We have 5 answers only so far. So can you guys log in again? Is it done? You're done. Okay, what about the rest of the class? You done? Done. Okay. And don't play with me because you know I wanna make things sure that we scoring well. Okay, what about the rest? What's that? Okay, I think it is going to be okay then. So I noticed a little while back there were 20-something online participants, but I don't know if they're able to log in or not. And I also cannot see if there were any comments from their side. Let me see YouTube. YouTube seems to be healthy. Audio is very weak. Okay, I need to look at that again. So audio is very weak. Oh, that's right. So you can only hear me in one side. How come you only hear me in one side? Let me. Audio. Okay, still one side only. What should I do to make this up? Is it this making any difference? No, still no. Enable. Okay, let me see this one. Still not different. No, it's the same story again and again. All right, I think that I need to go this class until we have a break somehow differently. Usually this works like no problem whatsoever. Oh, I think that maybe this is simply because, no, that's not the explanation. Let me try this. Yep, now it's better. So this mic was a broken mic because I see that, oh, it's still not broken mic because now it comes on another end. So what if I use like this, using two mics? So this could introduce quite a bit of the echo. So let me ask from online participants. So is it still cannot connect to Socrative? Okay, some of the guys are unable to connect to Socrative. I need to check that too. But anyway, so these are the results. And look at the number of answers is at 34. Thanks, guys. Appreciate this. Appreciate it. Very much appreciate it. Yeah, this is the way to go. This is how we're going to... Okay, can we make an agreement like this? From this on, every single Socrative is going to be 100% success rate. Thanks. Appreciate it. Big time. All right, so let's continue the story then. So what next? So let's introduce another way to describe the rotations in three-dimensional space. This is actually not another way. This is not the new way, but it's a method based on Rodriguez equation. Big problem in Rodriguez equation is that the usability is not great. It's not great because these parameters are not telling you much. Their physical interpretation is almost like non-existing. So let's make an attempt to improve the usability. This is not going to be a great result, and this is not going to be a great attempt, but still better than this original Rodriguez equation. So let's do the following. So let's substitute this kind of the trigonometric relation to original Rodriguez equation. What's going to happen as a consequence of this is that you're going to have a Rodriguez equation, put it in a writing like shown down here. And then we just start calling different components by different names. And what are these different components? We're going to start calling them as follows. So we're going to call something as a theta 0, and something that is called theta 0 will be cosine theta divided by 2. So it's going to be this guy here. And then there's going to be one component that we're going to call like as theta 1, and that's going to be first component of vector v multiplied by cosine theta divided by 2 divided cosine theta divided by 2. Give me sine theta divided by 2. This is going to be our next naming. This is a naming game, nothing but the naming game. All right, then comes theta 2. That's going to be v component 2 multiplied by sine theta divided by 2. And then finally theta 3, which is a v3 multiplied by sine theta divided by 2. And now with help of this naming, we can eventually write our rotation matrix using this pretty clear 3 by 3 description like this. Okay. Now, how much this is different than original Rodriguez equation? No different. No difference. Still this concept remains the same, so there's no difference whatsoever. The only difference is that now we're using these parameters theta 0 all the way to theta 3, so which is a total of 4 different parameters. But again, usability is not enhanced too significantly. But still, you know, at least you don't have to deal with directly with the vector v components. Again, we have 4 parameters. We still have to have a constraint. Constraint remains the same in the previous case, because look at where these components are coming from. So they're coming from the vector v components. And the vector v, again, have to remain as a unit in length. So that's going to be your constraint. In Rodriguez, Euler's parameters, this constraint can be expressed in terms of Rodriguez Euler parameters. I keep on saying Rodriguez all the time. Euler parameters in such a way that you're comparing the length of this vector, and this length have to remain to be 1. And that's your constraint. You can divide this. This is exactly the same story than in the previous case. There's no difference whatsoever, because once you substitute the information about thetas to this equation, what is going to be left is exactly the same, that the vector v have to be in a unit in length. Same story, different wordings, not the difference at all. All right, so that's Euler's parameters. Euler's parameters are very different than Euler's angles because they are conceptually coming from different procedure. Euler angles coming from these successive rotations, whereas Euler parameters coming from this fact that you have a vector and the assisting vector, and Euler parameters eventually are describing these assisting vector components, vector v and angle theta. So that's how it is. Shortly about their properties of rotation matrix. You know, this is orthogonal. It's describing the coordinate axes, and because it's describing the coordinate axes, if you're building the vectors out of the columns of 3 by 3 rotation matrix, these columns will be unit in length, first of all, and they will be perpendicular with respect to each other, as is the case in three-dimensional coordinate axis system. So each of these axes are perpendicular with respect to each other, and they are unit in length. That's it. Now there is a one thing that, like, if for some reason if you make your computer simulation code using 4 parameters and you are forgetting to use this constraint equation. So what happened as a consequence of that is that these vectors still remains to be perpendicular with respect to each other, but they are no longer unit in length. And that's going to be a big problem because this mapping will increase or decrease the body dimensions. And that's, not, of course, not happening in reality. So you make sure that you have to have this constraint equation all the time with you. What's up with this blinking business? Is it because of the loose connection here or here or here? Maybe that was a consequence of that. All right. Now, because of this orthogonality, if you take a transpose of your original matrix, multiply that with the original matrix, you're going to get the identity matrix. Identity matrix is something where diagonal components are ones, off-diagonal components are zeros. That's how it looked like. And of course, in three-dimensional space, rotation order is very important. You cannot change that. You just cannot. Okay, robot kinematics. Now we are moving to a bit more pleasant topics. We're going to shortly visit in robot kinematics because you guys are taking classes like robotics. You are not taking any classes about Heikki's or Wu's robotics. None of you guys are taking any robotics classes. Seriously? So is what? Because is that was that like an automation and control package? And you are not taking automation and control package. So what is a package? You take a digital engineering, but you need to take another one too. What's another package you take? Automation and control. So then you do take these robotic classes. You sure? What's the name of the course?
Probably it should be Advanced Industrial Mechatronics or Control of Mechatronic Systems.
Control of Mechatronics. That's a Hendrix course.
Yeah.
You already took the class.
I think we have this class this semester.
Okay.
It's going on.
So it started this semester?
Yes.
Okay. The lecture started already, or they will be later this week? They started already. Okay. The Hendrik is a fantastic teacher, so I'm sure you're going to enjoy it big time. But he's teaching a little bit about the robotics. All right. What I'm planning to do is I'm going to take this understanding you build about the three-dimensional rotations and explain a little bit about how you can make a use of that in robotic systems. Of course, my examples are industrial robotic systems, like different simple robotic systems you can find out there in the machine shops. But more important, I feel, is these humanoids kind of the robotic systems, because you see that these humanoids are evolving quite a bit, And they are making predictions that sometime soon is possible that humanoids can do some of the tasks in the machine floor or the machine shop floor. I don't know if this is really going to be the case or not, but there at least is an area that is evolving quite a bit. And then maybe there's another application that you are really want to have a kinematics rapidly, and you're not willing to use a multi-body system dynamics because that brings you too many parameters. So how you can make this happen in a robot kinematics, in an application of robotics, that I will shortly explain to you next. Okay, just, it's basically no new information. We're going to make a use of this equation that we've been using in a multi-body system dynamics. We're just going to reorganize the entire description. This is our kinematic equations. And in a robot kinematics, we're going to start using something that is called 4x4 matrix description. It has no better name than that. And of course, not the big surprise that this method comes because method is based on 4x4 matrices. And basically what you do with this procedure is that you take this component, you are putting them inside of this 4x4 matrix representation, that's it. Why this is nice? Because this is kind of automate your kinematic description. So if you need to have a kinematics about the different robotic system, mechanical system, with help of this 4x4 method, you can build it like no time at all. How that happens, I'm going to explain you that momentarily. All right, see, these are, by the way, the questions. And again, you have an access to these questions later once we have a Moodle base up and running, which is not yet the case, but it's going to be later this week. How the 4x4 matrix representation can be used in a robot kinematics. Explain the method based on Dynavik-Hartenberg matrix representation, 4x4 matrix representation. So you're not guys aware of this Dynavik-Hartenberg. Okay, you're going to learn that a little momentarily. All right, so the robot kinematics is basically almost like a multi-body system dynamics. So basically, you do know how the different bodies are, how they are oriented, how they are translated, and then you would like to know where the end effector, where that is located at, how that is oriented to. And that's basically what you're basically interested in. There is a major difference between the multi-body system dynamics and robot kinematics, because basically your target is reversed. You are usually interested in how is your end effector located and translated to. And then you would like to see how to make it happen with rest of the bodies in your system. So basically, this is something you do know, and the rest, how the robot system is configured, what are the angles, relative angles between the robot bodies, those are not known. And typically, there are multiple different ways to reach the one configuration of the end effector. And that's simply because most of the robotic systems are redundant. Human body is a good example about the redundant system, because I can put my finger to this point, this orientation like this, and I can, I'm not too flexible, so I'm limited like how many different ways I can happen. I can do the same, but basically I can point, this corner, and rotate my other angles. And this is a redundant system. So I can reach the one configuration of my finger in a multiple different ways because of too many kind of like degrees of freedom. The human body is a very problematic because human body has too many actuators too. You know that human body consists of more than 1 million different muscles. Well, it's less than 1 million muscles, but there are a lot of different muscles. There are sometimes, some of them are accelerating, some of them are decelerating the system. So it's not just a redundant system, but also having too many actuators, which typically is not the case in mechanical systems. It's very common that you have like just to give you an example, like you have a hydraulically driven crane, you're lifting this mass here. Say you have one actuator to make it happen. So 1 degree of freedom, each of the degrees of freedom are actuated by one actuator, hydraulic cylinder in this case. If this would be a biomechanical system, a human muscle system, it would be probably looking like this. There will be multiple different actuators. Some of them are pushing, some of them are decelerating, this is how the human is built. So not the great build. I don't know. This is but these muscles are really cooperating well together. It's hard to make it using mechanical actuators. All right. Anyways, back to where I was. So I was about to explain, like. Oh, by the way, one more story about the biomechanics. This is one of the great challenges in the biomechanics because there's so many muscles in human body. Some of the biomechanical models are driven by muscle forces. So you really need to know each of the big muscles in your body, how they are producing the forces. Are they actually producing the forces, or are they accelerating, decelerating? What is their role? And that's not an easy thing to do. And this is usually something that takes a lot of computing to understand how the muscles are behaving in a biomechanical system. It is possible to do that, but it needs a lot of optimization procedures. And eventually, I don't think it is going to be exactly the same that in a human body because it's so complicated thing to do. All right, so that's what we know about biomechanics. And here we would like to know, okay, this is where the end effector is located, how you can make it happen with help of these rotation matrices and translations too. So basically, you know what this is supposed to be, but you do not know the rest. And you don't know what is this one, what is this one. Those are the question marks. And now if you can reach one configuration in global coordinate system with multiple different ways of R's and rotation matrices, then your system is redundant. Most of the robotic systems are redundant. So you can reach one location in two different configurations. All right. But that's what we're aiming for. In robot kinematics, this is what we are really interested in. But we can get started from the forward kinematics. So we do know each of these components, and then we're just comparing how is this guy here. Makes sense? By the way, any comments, questions so far? Anything you would like to discuss with me? Or it's like you're happy? Biomechanics, nothing that this time. Humanoids. Of course, another, the humanoids is something that is a big evolving field, but another one that is a pretty big topic at the moment is this exoskeleton system. These are machines that are like clothing systems that are helping you to perform certain things. So they're like if you need to install something in a very uncomfortable position upright in your head, you can have some assisting devices. Some of them are passive, some of them are even active ones. It helps you to have a bigger muscles. So if you need to lift something, you can make it happen with those exoskeleton systems. So, and of course, one of the big reasons to do that is the military applications. So you just basically, what is the movie that you're kind of inside of the robotic systems and it gives you an enormous amount of forces? Is that like a Transformers or what's the movie like? You're sitting inside of the robotic systems. Which one? Yeah, but almost like in the movies. Of course, not in the same scale because in the movies those are like a size of the apartment building, so they are not that big. But they can be almost considered as a closing system, and they help you to perform certain tasks. All right, but anyways, back to this. So this is what we are getting started with. We're going to start using this method that I already mentioned. So it's method based on 4x4 matrices. A 4x4 matrices, to cut the story short, goes like this. You take these components and you relocated them in a 4x4 matrix. Rotation matrix is going to be in a upper left corner of your 4x4 matrix. So it's going to be located here. That's going to be where your submatrix will be located at. And then it's going to be R, which is a vector consisting of 3 components. That's going to be located in the upper right corner. What is going to be left is 1 row, because this will be here having 3 rows, 4 columns. You need to match the number of rows and columns. You need to add 1 more row here, and 1 more row will be added in a way that it's going to be fully zeros, and just the diagonal component, which is called scaling component, that's going to be 1. If this is going to be any other number than a 1, it's going to scale your stuff. Make them to be bigger or smaller when you do this 3x3 mapping business. So which is not, again, what happens in reality. Anyway, so it goes like this. Once you have this 4x4 matrix, then you can make a use of that pretty much in a similar way that you're adding here vector U bar. You just have to have some modification to vector U bar, and here we are not going to call that a vector U bar any longer, but vector P. And vector P consists of vector U bar components, and these components are the ones that are located here in a vector that is having 4 components in total. They are located in a first, second, and third locations. Fourth location, again, is a scaling component, will be equal to 1. That's it. End of the story. Why this makes sense? So why it makes sense? It makes sense because this 4x4 is a combination of translations and rotations. And then when you make a use of that, you can move like here, you can take the body orientation into account. With the vector P, you can find easily where the body or where the point is located at. So that's kind of the beauty of the method. And it becomes to be pretty efficient when you have a multiple coordinate system, multiple bodies connected together, which we're going to revisit momentarily. But let's take a look at the simple example. So we have here the coordinate P, coordinate system B, that is rotated 30 degrees with respect to global coordinate axis Z. And that's going to give you, sorry that the numbers are not clearly so. It's going to give you this kind of the 3x3 rotation matrix based on, for example, aerial angles. You don't need to worry about what method you're using, but here I recommend you to use Euler angles for the reason that I will explain you momentarily. All right, and then coordinate B also translated 10 units along the global coordinate X coordinate axis, 5 units along the global Y coordinate axis. So these are the R components. You just take these numbers, substitute it here. This is what you can compute based on this information. That's it. That's all you need to know. It's about reorganizing things, nothing but reorganizing things. All right, and then you have this vector P that was given also in these assignments. Then you put the numbers here, and this is going to tell you what's going to be the final location of point that you are interested in. But again, power of the method comes when you have a multiple coordinate systems that are related to each other. That's when you can really make a use of the method. Because basically what you do is that you're getting started with a global coordinate system, then you have a first transformation matrix that moves from here to the second coordinate system. It takes its orientation into account too. And then you are here, when you're moving on from this coordinate system, again, you can use the same kind of 4x4 matrix representation, and you can put yourself here. And this is going to be this one here, A to the D. And again, from one coordinate system to another, each of them are describing this 4x4 matrix representation. And when you just keep on adding them together, eventually you're going to get where the end effector is located at. It doesn't matter how many different coordinate systems you have under your way. You just keep on multiplying all of them together. And it's simple business like this. And that's where the beauty is coming from. Because now you just look at how the system is configured to, and then you just start applying these 4x4 matrices. You multiply them together, your kinematics is ready. So it doesn't take any time at all. It takes some time, but not much time. All right, robot kinematics. There's one note that I need to mention to you, and that is the fact that in robotic systems, like what we describe here, we're kind of assuming that all possible translations and rotations can take place. In robotic system, that's not common. That doesn't happen at all, because robotic arms are connected together in a very limited ways. Typically, they're connected together via translational joint, rotational joint, few other combinations, and that's it. And when you make a use of that fact, then it becomes to be very much limited, and then really this method becomes to be useful. And basically, because look at this, this is a typical robotic system. So there could be this body connected together via revolve joint. This body and this body connected together via translation and rotation. Combination of things, and when you limit yourself to these motion possibilities, relative motion possibilities to be more specific, then it's really easy to start building the kinematics. All right, and that's what this Dynavik-Hartenberg method is about. One more note. I mentioned that it makes sense to use Euler angles. Yes, it makes sense to use the Euler angles because right now we are not considering arbitrary rotations, but very limited cases. Limited cases where the singularities doesn't really are a big problem. So that's why you can make a use of the simple method like Euler angles. Okay, all right, so this is the way it goes. So you can look at the different kind of joints. Cylinder joint, there's two variables because they can rotate and translate with respect to each other. Like here, they can go like this, they can rotate like this, relatively with respect to each other. Revolute joint, they can only rotate with respect to each other. Translational joint, they can only translate relatively with respect to each other. And now, when you start making a limitation to this matrix based on three motion possibilities, that's when you're going to get Dynavik-Hartenberg method. Dynavik-Hartenberg method is based on 4 parameters that are describing these different motion possibilities. But they're basically coming here. 1, 2, 2 plus 2, 4 together. And this is how it is. This is a little bit, I go fast because I don't want you to be too much worried about the details. You just focus on the big picture. The big picture is just what I just explained to you. You are taking these 4 parameters into account. These 4 parameters will be introduced to you next. And they are like length of the body. This one. This is a common length of the body. This maybe in a certain cases it can be the one that is variable. And then there's an angle between the, how the angle of the body to new body is consisting to. And then there's going to be distance between the 2 bodies, neighboring bodies, how much they are relatively rotated with respect to each other. Those are the cases. Now what I will do is that I will introduce each of these 4 parameters to my multibody parameters. And these multibody parameters, if you think about the length of the A, it's a simple case like this, it's going to be this one single Rx that is going to be a variable. Rest will be zeros. Once you substitute that information to your 4x4 matrix, which is rotation here, this was R. The only one that is going to be non-zero is this guy here. End of the story. Then you're going to take another one, which is going to be this time the angle, and the angle obviously is angle theta. Again, you substitute that information here. All the rest will be zeros. All the rest are zeros. This is how your 4x4 matrix in that particular case look like. 2 more components to go. Then again, the distance, which is a translation. This time, this is a non-zero component. When you substitute all information here, this is how things look like. Last one, which is angle theta here, this one here. When you substitute that information, it's going to be like this. So final 4x4 matrix representation reads like this. It's based on 4 parameters. 4 parameters. Now the only remaining thing you need to do is that you need to give these 4 parameters to each of the links, each of the bodies in your robotic systems. And when you do so, then you're just multiplying these 4x4 matrices together. That's your kinematics. Your kinematics is ready. Let me summarize one more time. In robotic systems, you have to give these 4 parameters to each of your bodies in your robotic systems. Then once you have these 4 parameters, then you can build these 4x4 matrices for each of the bodies. And the final kinematics, you just can get it by multiplying these matrices together. You able to follow me? Okay, so it goes like this. These are the summary of the parameters. It goes like this. Here's an example. This is a double pendulum, so it's not really too complicated robotic systems. But again, good example what we can do with this method. So we can make a use of the method by taking the body 1, body 2, I'm building these 4 parameters, each of these bodies. These are the parameters corresponding body 1 and body 2. Okay? The only difficulty is to build these parameters. Once the parameters are ready, that's it. You're good to go. All right, the first parameter is not a variable, it's just length of the body. Then there's going to be how much they're rotated in out of the space, That's going to be 0. Then this one was how much they're moving like off plane direction. That's going to be 0. And that's how it's going to be relative coordinate between them. That's going to be angle theta 1 and theta 2. That's it. Those are the parameters you do. Once you have the parameters ready, then you're building 4x4 matrices for each of these bodies. This is for body 1. This is for body 2. That's it. Final kinematics, meaning that where this is located at with respect to this coordinate system, you can get it by multiplying these 2 matrices together. This is where the final configuration is. This is telling you that. This is telling you the final orientation. Pretty beautiful. Pretty nice. I would say that this is quite useful because, again, you're counting how many bodies you have in your robotic systems. Once your count is ready, then you build a matrix table like this. You are creating the rows for corresponding each of the bodies, giving these 4 parameters for each of the bodies. Then you substitute these parameters. This becomes to be so messy that I need to. Can I get started the story from the beginning one more time? Okay. Yes. No. Yes. Okay. So you're just counting how many bodies you have in your system. This time is 2. You're building this table. Each of the columns in your table corresponding the bodies. This is a body 1. You're creating these 4 parameters for body 1. You're creating the 4 parameters for body 2. And then you take these parameters, no thinking whatsoever. You take these parameters, substitute this 4x4 representation. That's it. 2 times substitution, and you multiply them together. That's your final kinematics. Pretty efficient, but limited in a sense that you can only play with these 4 parameters. You cannot do more than that. That's your limitation. All right, and then there was also a little, to prove that this is correct, I did the same based on the multibody system dynamics. We can trust that this is correct because it was correct. It was correct. All right, then we're going to have a break because you need to get some oxygen. You need to get some rest because then we're going to make the final step about 3-dimensional dynamics. We're going to find out why this is the case. And this is going to be one of the questions that you might have in your written exam. So basically, why these rotational parameters and their time derivatives are not angular velocities. So why this is the case and how you can make them to be related. This is where we're going to get started right after the break. So can we have like only 5 minutes? 5 minutes. Good thing. And let me see what's up with my mic system because it's not willing to collaborate so well. Well, let me take a look at the comments from the online participants. It works now, so there is no complaint. Okay. Five minutes. You can go, but you don't want to go. niistäkin jutella, jos haluat. Eli ehkä ette, mutta niin, ei se niin väliä, voi sitä siltikin, niin, vaikka ette halua jutella, niin minä voin jutella niistä. Mutta nyt se, joo, työtilanne on se mikä on. Siihen ei varmaan auta muu lääke kuin hakea. Se on niinku. Mutta sitten on toisaalta niinku sillä jännä, että so this, by the way, this discussion was about how is the job markets in Finland because they are disaster at the moment. They are really disaster. So it's really not easy to get any kind of position, even a summer position out there. It's super difficult, super difficult. But of course, what helps a lot is that you apply. If not applying, no one will never come to your door and twist your hand and force you to come and work. That's not going to happen. So you need to be active by yourself. Have you guys already applied your summer jobs?
Yes, I have been applying for the summer job for the last 3-4 years. I haven't received any position yet.
Really?
And,
But have you been that long time in Finland?
yes,
All right,
I've
so
been in Finland for the last 5 years.
5 years. And you've been applying every single year.
Yes.
But now I think
It's my first year in
yeah,
lab university. I was doing my bachelor's in lab university.
right, right.
I've applied for all positions.
Yeah.
Last year I got one position in the university as a supervisor for the summer internship.
So what was that?
Summer internship supervisor.
Okay,
There is a problem.
all right. Yeah, I think it helps a little bit if you're master level students that you're an engineering student, because engineering seems to be one of the big promises in Finland right now. All others are suffering even harder than engineering, and even engineering is not doing so great. But it really is important to apply. Important to apply, and you guys need to make sure that whenever you're applying, you need to have a really decent looking CV. Make sure you're using AI in your application process, because they're reading your applications based on AI. So AI, so they came along together, so that improves your chances. Of course, you need to tell the ChatGPT that write this in a way that it doesn't look like AI written stories. And then they are, checking this. It's like, evaluate these applications such that it's not looking like AI made evaluation. So it's AI all over. Yeah, but it's important to apply. So have you guys looked at this this workbook, this technology industry workbook? Tech. That's the most important asset. Right. Yep. But it's hard because there is so many applications. It's hard to make the application such that it differs from others because everyone is using AI, everyone is making beautiful applications. So how you can make the one that is looking different than your fellow students' applications? I don't know. Okay, should we get back to this subject matter about how to apply the summer jobs next week? Because this is pretty much the time to do so. Because you wait another week or 2 more weeks, most of the positions started to be filled. Even though the application period may be ending sometimes in February, March perhaps, but as soon as they find a proper candidate, they're just going to go. They're going to make a deal and that's it. Good. Okay. Have any one of you guys already got the positive call? You got the call from the sweet spot, other than you still bending. Yeah. Also, you guys notice that there is this open positions in university. You noticed?
Really?
Yeah, there is an open positions in university, summer trainer positions. And I think that it makes sense to apply pretty much right away. Although that they are not going to select anyone before their deadline is going to be ending. But still, make sure that you're applying as one of the first candidates to apply. But you guys, you know that there's open positions in university, so you have seen it, but you haven't.
So where can we exactly check those open positions?
Where can you find those open positions? I don't know. Where can you find those open positions? Because they are not in the university website. They are not there. Because this is internal call. So these positions will be filled by LUT students, not students from Aalto or any other no-good university. So it have to be LUT students. But where to find them? Is it intranet? I think it is intranet.
Internet.
Intranet. You have an access to that intranet? But so you might need to check your inbox too, because maybe there was something mentioned in your email. I think they opened the call already. I think they opened the call, I'm saying in December. Okay, so why don't you go and check here. You have an access to this website, this internal website, this one.
I think this is for employees.
Okay, so not this one. So where can you find this then? Job teaser. But you see, is a job teaser is a, okay, job teaser LUT. Okay, this one.
Yeah.
LUT locking. Okay, I have not been here. Accept. Should I activate this? So is this the way that I can?
You can find it at job at LUT.
What's that?
You can find it at job at LUT.
Yeah, I could find something, but it seems that there's. What should I do next? Oh, I don't want to go any further than this. This looks pretty complicated. But take a look at this one. If you're not able to find it there, then jobs. But I don't think it is there because this is internal call, and that's why. So, all right. Okay. But again, it really is a time to apply. This is because if waiting another couple of weeks, that may be already too late. And it's not big surprise because some of the positions are already opening or getting active to be in the beginning of May. And May is not that far off, honestly. Although that is look like the three-dimensional multibody dynamics, or more specifically, three-dimensional kinematics. And I'm not going to deal with the entire story. I just want you to be aware of what is a big deal about the whole thing. And then we're going to move on and discuss about flexible bodies. And the flexible bodies is entirely another subject matter. And we're going to learn the method where we're actually combining the finite element formulation and multibody system dynamics. And this is going to be something that takes us a couple of weeks to do the entire story, because I would like you to be aware of what the finite element method is about. Because I know that there is a fantastic teacher, Marko Matikainen, that is currently responsible for finite element courses, and he's really good in that. But I would like you to be aware of the basics of finite element, because often you hear that to be called like there is something like there is a nodes, and between the nodes there's nothing. It's just the springs or something. Finite element method is not that. Is not about springs. It's something completely different story. And what is this completely different story that I will shortly explain to you. And then I have some stories about how I've been struggling to build the different kind of finite element elements. So element technology. All right. This is a question. How inertia tensor is related to acceleration of rotational. Okay, this is actually not the question that I can ask, because I'm not planning to go all the way to inertia tensor, but I'm going to just want to focus on this relation. Angular velocities and time derivatives of rotational parameters. This one here, just for your information, this one here could be the one that is based on Euler angles, and then it's going to be 3 parameters that you can differentiate with respect to time. They could be based on 4 parameters, like in the case of Euler parameters or Rodriguez equation, and again you can differentiate those with respect to time, but they never ever becomes to be same than angular velocity. They just will not do so. All right. Okay. Here's a story that is just put you in the deep end of the swimming pool. So this is kind of the story in nutshell. Basically, what I wanted to do here is that I want to take this equation, this is what we learned in the case of kinematics, and I differentiate that once with respect to time. And when I do so, I'm going to get this equation. In this equation, obviously, when we're dealing with the rigid bodies, the component here in the middle will be eliminated. And why that is the case? That's simply because the vector u bar is a constant vector. So it's not the function of time. So when you differentiate the vector u bar as with respect to time, that's going to be 0. And that's why this component will be eliminated. What is left, though, is going to be this one, which is a translation of velocity, and then something where you differentiate your rotation matrix with respect to time. And now I'm not going to show you what's going to happen when you do that, but basically what you're going to get as a result of that is you're going to get the angular velocity vector. Angular velocity vector expressed using the skew symmetric form. And again, don't get confused about skew symmetrically, because skew symmetrically was just how to take a vector, how to put these vector components in a 3x3 matrix. Nothing but to substitute some procedure. All right, but again, what comes out from this is an angular velocity and rotation matrix. This is the same that happened to us in a case of planar case. The difference here is that this time, this guy is not the scalar component, as it was in a planar case, but it's a vector. Because vector, of course, because we have here 3 coordinate axes. So the angular velocity is respect to each of these 3 axes. In a planar case, it was only this one here. So it's a scalar component. Scalar is a single number, vector is a 3 numbers. Okay? All right. So here's an alternative. What you can do is that you can express this in terms of body reference coordinate system. So you can map velocity from body to global coordinate systems. Doesn't make much of a difference, so it's irrelevant. All right, but what you're going to get as a result is this. So this is how things look like. So you can write this. What is this? So like why this is? I think yeah. Don't look at this too much because I'm going to take this vector u bar off. So this is what I'm going to get as a result. So I have my angular velocity, my rotation matrix, and vector u bar. Now, really what I wanted to do is that I wanted to express all the kinematics using my generalized coordinates. So let's look back. What are the generalized coordinates? Those are the ones that are telling you the translation and orientation of each of the bodies in my system. In a planar case, they were pretty straightforward. They were Rx, Ry, and angle theta. All right? In three-dimensional space, they are almost the same, so they're Rx, Ry, Rz, and then depending what kind of rotational parameters you use, they could be, if using Euler angles, it could be like this, the body A, these are your parameters. So these are 4 parameters. Now the problem is that the way you're expressing your velocity like this, these guys are not here. They're not here because you only have this angular velocity. This is clearly here, but these guys are missing. We need to find the way to express them because otherwise we just cannot solve the equations of motion. And we can find it out by using something that is, first of all, there's no method so far invented that relates directly these 2 parameters. Again, let me write it one more time. So your generalized coordinates in 3-dimensional space, they were like, let me just call this a theta 1, theta 2, theta 3. So when you take these guys, you can call this vector as a theta. And when you differentiate this vector with respect to time, you're going to get the theta dot. But this theta dot is never same than angular velocities. With respect to body coordinate system or with respect to global coordinate system, they are just not the same story. And if you're able to invent a way that you can put these to be equal together, like this, you can, if you're able to think about this, and if you're able to find a way to put them, way to describe, basically you need to find a way to describe these generalized coordinates in a way that they become to be same than an angular velocity vector. If you figure that out, you come to my office, we work together, you're going to get the doctor degree from the rector's office same day, and then you come back to my office, you say, okay, pack your stuff, go someplace else because I'm going to occupy your office. Then, of course, I'm going to leave, and then you're going to take, oh, no, you're going to go better university than LUT University. You're going to establish a professorship in a better university, and you become to be world famous. Not much. Only thing you need to do is that you need to figure out this equation, and you're going to be super famous. Think this. But don't invest too much time, because there have been quite a few others doing the same thing, not successful so far. But again, if you have any spare time when you walk in your apartment, you might think, okay, this is the way to go. Okay, how you can relate these two things? You can relate those by using something called G matrix. This G matrix comes the way that you define these three rotational parameters. And again, define, like I say, it depends how you're defining these three or four rotational parameters. This G matrix can be built for each of these cases. For each of these cases. How they look in the case of Euler angles, they look like this. So G matrix is like this. And if you look at the columns here, they're actually telling you how the rotations are taking place. Because obviously the first column here is a z-coordinate axis. If this angle here, if this is equal to 0, this is obviously x-coordinate axis. And if this one and this one are zeros, this is obviously z-coordinate axis. And this is the one that relates your generalized coordinates and angular velocities. And this is what you need to use continuously in your computing. And here's where the problems are coming too, because this is the very problematic matrix you need to keep on all the time with your computing. So it's just significantly more challenging than anything related to two-dimensional space. Now, so if somebody's asking, why is that three-dimensional space is so much more complicated than two-dimensional space? Answer is that you have to deal with the G matrix to be able to relate angular velocities and generalized coordinates. That's in short. And that's where we're going to close. Now, we are not going to score 100% for this in-class quiz. This is a G matrix is important because it couples the local and global coordinates. It couples the angular velocity vector and time derivatives of generalized coordinates, describe inertial properties of the body, couples global and generalized coordinates. These are the four options. And I'm going to put the Socrative on, and then I'm going to leave this three-dimensional thing away, and we're going to focus on something different than that. Okay. Socrative is here. How come it's so hard to use this mouse? Here, this one. Oh, it's here. Okay. You guys are good to go. Can you see this? Yeah, it's clearly visible. What do you think? I think that like if we score more than a 60% of the success rate, then I'm going to be happy. Less than 60 will be not cool. 60 will be okay, acceptable. Statistically, it could be 25. Like if you just randomly enter your answer, but we'll see. We'll see. I think at the last time, don't remember how many answers we got last time, but I was thinking. It was like, was it 30-something or 30-something? Okay, I'm going to leave this to you guys to think. And then I'm going to move myself to flexible bodies. Flexible bodies, which is a complete another subject matter. And what is the deal with these flexible bodies? Well, the deal is this. We've been all the time assuming that there's no mechanical deformation in the bodies we're dealing with, which is, of course, not the reality, because every single body is, end of the day, deformable body. there's no such thing like rigid bodies in this planet, because regardless how thick steel is made out of, I can always introduce forces big enough that I can introduce deformation. And the deformation doesn't necessarily need to be that big, but still it deforms. One clear thing that demonstrates you that bodies are always flexible is that they do vibrate. Even when you have a highest possible, the biggest possible bridge or a building or whatever, you can hit that by a hammer and you hear the noise. So the noise tells you that it is vibrating. And it will not do so if it would be entirely rigid. So the rigid bodies is not what you can find in reality. Now the big question, of course, is that, okay, how is it that we can describe the flexibility? How is that we can describe the deformation of bodies? And we can make it happen by using finite element method. Finite element method is very often used in the strength of materials to figure out strength of the materials, strains and stresses. Basically, that's what we are after when using finite element method. And then also another big question is that how to describe it and when it actually makes sense to describe something to be as a flexible body. And that's even harder question, how to comparing like how to describe bodies to be deformable, because there is no clear rule how you can describe something to be, when something needs to be modeled as a flexible body instead of rigid bodies. There's no clear rule, and even today there's no clear rule to make it happen. It is based on something that is called your engineering sense. Engineering sense and common sense are relatives. They're not the same, but they are having the close relation. Engineering sense is, if there's common sense here, engineering sense is above the common sense. Why this is above the common sense? Because you have to be an engineer to be able to use the engineering sense. And that's why. And the common people are confused, like, what is this deal with about engineering sense? You can always, you have to have a proper education to understand that. Honestly, you can create any kind of method you want, because how to select the bodies to be rigid or flexible, you could just select that randomly, because there is no really way to know that. No really way to know that. Okay. Now, another thing. We concluded already when we look at the rigid bodies that body consists of very high number of particles. Same holds for flexible bodies. So it meaning that, even this one is consisting of infinite number of particles. Particles can move relatively with respect to each other in case of flexible bodies. And we just cannot do that. We just cannot take all these millions of particles, trillions of particles. What comes after trillion? What number comes after trillion? I don't even know. So billion, trillion, trillion particles. You cannot take these trillion particles and model them, because no computer can handle that many degrees of freedom. That's not just possible. So what you need to do is that you need to use something that is called discretization, meaning that you are not taking all of them into account, but some of them into account. You are dealing with something called number of degrees of freedom. Basically, how many different ways structure can deform. That's what this is telling you, shortly speaking. Now, if previously we were looking at what are the different ways that the structure of the body can move, now we're also looking how many different ways it can deform. That's what is called discretization. And there is a limited number of ways it can deform in computational perspective. In theory, it can move any ways. There is no limitations whatsoever. All right, so my first question is this: like when a body deformation needs to be accounted in a multi-body system applications, and there are options are when large forces are applied to the system. Like I mentioned, there could be very solid big buildings, and you might assume those are rigid. You take a hammer, you click them, and you hear the noise. So there's no way to use that as a way of thinking this. Depending on really of how big is the forces, because there could be significant amount of forces. So even the most solid built structure can deform. So when the natural frequency of the body is low, this is one possible way to go. when the slender structures are considered, like cables and so, the final thing is that there's no general rule to make this decision. What do you guys think is the correct way? I was a little bit unclear in my explanations, but let me just take a look like how well you do in this case in Socrative. So let me just take this one. It's this guy here. Okay, success rate of this one, I was saying 60%. You guys have much bigger brains than I thought. My apology, because this, let me see. There's one incorrect answer. Couples the global and generalized coordinates, which is not even very incorrect answer. That's a pretty good answer too. The correct answer is, of course, the option B, which says angular velocity, vector, and time derivatives of generalized coordinates. Okay, the next one. What do you guys think about what is the rule to select when the body needs to be modeled as a flexible body? This is not easy. That's the hardest question, hardest in-class quiz of the day, for sure. Okay, so the number is 12 and counting. 13. Okay, I'm going to leave you guys to think about this, and I'm going to revisit that momentarily. Now, here's something that is important for you to be aware of, because now we are not discussing about reality, but we're speaking about computational aspects. Okay, so now you say, okay, the body needs to be modeled as a flexible body. Then you have two big choices, or one big choice to make. You have to be able to assume if your deformation is small, meaning linear, or is it going to be nonlinear, geometrically linear or geometrically nonlinear. And those are conceptually very different stories. And to be able to explain how they are different, we need to take a look at the cantilever beam. Cantilever beam that is loaded by a free end. So here's a free end that is loaded by a force F. So when I'm introducing the force F to the free end of the cantilever beam, what's going to happen is this. The body deforms according to this figure. And this is basically what you can see in a reality. This is the case. So it's deforming like this. And when I'm making this computing, I'm assuming that there is a relation between the displacement. The displacement is like this one here. And the displacement is, of course, a function of x. X is this one here, which is a coordinate along the length of the cantilever beam. So each of these points have a different U, deformation. How I'm relating to deformation and strain. Strain is how much the material is experiencing the strain here. This relation can be linear, which limit ourselves to small deformation. Then we cannot deal with the large deformation, which is unclear, like what's small, what is large. But let me try to highlight that by looking this cantilever beam, because when we're making this assumption about linear displacement strain relation, what's going to happen is that this free end of the beam will remain in a loading line like this. It's going to look realistic when it's a small deformation like this. But if it's large deformation like this is not, you don't see that to happen in reality. This is not the case, because in reality, you do see the deformation also in this x direction, because in reality, it's going to be like this. And this relation you can only take into account by introducing nonlinear strain displacement relationship. Okay, this is what's called kinematically nonlinear relation. And when you have this nonlinear, then you can deal with the large deformations. Where do you need a large deformation? Well, you need it in a case of cables, in case of clothings, tires, so on and so forth, airbags and so on. There are a few examples where you need that. But often you don't. Because in the cranes and such, is enough to be limit yourself to the linear strain displacement relationship. There are another relationship, and this is how you can move from the strain to the stresses. There's this famous curve about strain and stresses. This is what they teach already in the preschool. Not even in a bachelor level, this is clear. This is But how the steel material behaves in this kind of curve is basically like this. So it's a linear relation. There's a line that relates strains and stresses until it's not linear, until you reach the yield stresses, and then it becomes to be nonlinear like this. So meaning that if you keep on improving the forces here in a cantilever beam, you're first going to end up to be this corner. You keep on increasing the force, you're going to go this, that is called plastic zone, and then you take a force off, you come back, there's going to be permanent deformation. So your cantilever beam will look like this, even though that there's no forces left, because there is a permanent deformation. This one here is a material nonlinearity, typically never touched in dynamics. And why that is never touched in a dynamics, that's simply that, if you think about if there is a permanent deformation in a crane, what is that? That is a very low quality design, because if you lift something first time and it's immediately dependent like this and it lives like this, it's not going to be, it's not going to be making customers to be too happy, because your system is spent whenever you use it. Not cool. Or you're using your car, first time you close the door is going to be bended like this. People are not going to be happy. So you need to make it solid enough that there's not permanent deformation. So that's basically the reason that we don't deal this relation that often. We don't. Okay, I see that Mustafa is here. We only have a 5 minutes break. Really my purpose of this class is to try to keep this happy and casual, and we discuss about different subject matters. We can discuss about the flexible bodies, but we can discuss about summary jobs, about systems. We can discuss about humanoids and so on and so forth. UFOs, if you want. Not really my specialty, but we can discuss about different subject matters. I would like to keep this classes also exactly in a timely manner. We close it in a timely manner, so it's a time to close. So, before we go, let's take a look at this. How you guys think about this one here? 33 answers. You got it. You got that. You nail it. You nail it. Because exactly, there's no clear rule. There's no rule to figure out what needs to be modeled as a flexible bodies. There could be slender structures, but if no forces, it can be rigid. There could be low natural frequencies, but if not excited by low frequency forces, it's okay. So it's so case dependent that there's no rule. You can build your own engineering rules. You can look at the structures like this. Oh yeah, rigid. And the people are like, how come you know it? Yeah. That's why my salary is bigger than yours. Okay, good thing. All right, that's it. So next week, this is, by the way, the time and the place to organize the classes. Next week, Monday, this same place, same time, at 10 o'clock, 10:15 to be more specific. Okay, guys, take it easy, have fun, and respect.